In the last lecture, we covered a lot. We talked about electric flux, we talked about Gauss's law, and we did a simple example where we used Gauss's law to find the electric field around a point charge. Let's review and make sure we understand each of those steps. Let's start with the electric flux. If we have a surface area like this, and an electric field is penetrating that surface, as I've shown here at an angle, and we want to find the flux of electric field through that surface, we would use this integral of E dot dA. We could also write that as the magnitude of the electric field times the magnitude of dA times the cosine of the angle we get when we put the two vectors together. So I've shown my electric field vector in my diagram. The dA vector, the area vector, points normal to the surface. That's the dotted line I show here. So my area vector would point like that, and dA has that same direction. So the area vector is normal to the surface. E is going to be, I just drew it at some arbitrary angle, but the angle we get between the electric field and the normal is the angle we put into our cosine theta. So now we say, if the electric field is changing over the area, if it's not constant in magnitude, or if the direction is changing, if theta is changing, then this becomes kind of tricky. This integral becomes pretty tricky. The whole point of flux is to get us to find the electric field. We're using flux as a tool in Gauss's law to help us find the electric field. We already have a technique for finding electric field, right? We treat each little tiny element of the charge distribution as a point charge, and we integrate all of them over the charge distribution. We add up all the little charge elements in the charge distribution, what their contribution is to the electric field. And that worked perfectly fine, except that sometimes it gives you a really horrendous integral to solve. Now we have another approach that also has an integral that can be really horrendous and difficult to solve if the electric field is not uniform over the surface. So let's take a look at what happens if it is. If it is constant, if the electric field is constant in magnitude, then E pops out of the integral. And if the direction never changes over the surface, theta is also a constant. So this becomes E cosine theta integral of dA. And the integral of dA is just A, the area of our surface. So this becomes the electric field, the magnitude of the electric field, times the area, times the cosine of the angle you get when you put their tails together. So you see that this becomes fairly simple under certain conditions. When the angle between the electric field and the surface is not changing, and when the magnitude of the electric field is not changing. We want to find situations where those are true. The angle is constant and the electric field is constant. Well, that occurs when you have certain symmetry in your problem. So if we have spherical symmetry, if I have a charge distribution that's spherical, I've got a ball of charge, spherically symmetric. It's going to fill the space around it with an electric field that's spherically symmetric. So if I pick some surface to find the flux through, that's a sphere. We call that our Gaussian surface, right? If I pick that surface that's spherical, then let's see what happens. Every place the electric field penetrates that surface, it's normal to the surface. The angle is the same everywhere. We have a normal 90-degree angle, 90-degree angle, 90-degree angle. Those angles are all the same. Every place theta is the same. It's 0 degrees. The angle between the normal to the surface and the electric field vector is 0 degrees. We want the angle between the normal and the electric field vector. And because the electric field depends on r, if we pick a nice spherical shape around our charge distribution, E will be constant in magnitude because we're at the same radius on this red Gaussian surface. We're at the same radius everywhere. I hope you can see that under very specific circumstances, this becomes fairly easy to solve. Finding the flux becomes very easy. And therefore, Gauss's law will give us a way to find the electric field very easily. Now, there aren't very many situations where this is easy. Spherical symmetry is one, cylindrical symmetry is one, and infinite sheets is one. So those are kind of the only 3 cases where Gauss's law is really useful. It's true all the time, but it only really helps us, gives us an easier integral to solve than we would with our other techniques in those 3 cases: spherical symmetry, cylindrical symmetry, or an infinite sheet of charge. Since we're talking about flux, let's talk about why we have seasons on Earth. Often if you ask a child why we have seasons on Earth, they'll say it's because the Earth is closer to the sun at certain times of the year and farther away from the sun at other times. That's actually a logical explanation. If you've ever stepped up closer to a campfire, it's warmer, and you step farther back and you cool off a little bit. And if you happen to know that the Earth's path around the sun is not circular, it's elliptical, then that's a logical conclusion. The problem with that is that the Earth's orbit around the sun is barely elliptical. It's almost circular. If it was more elliptical, maybe the proximity to the sun would play a bigger role in our seasons. But it doesn't have much effect. We also have different seasons at the same time on Earth. One hemisphere will be in winter when the other hemisphere is in summer. And if seasons were caused by proximity of the Earth to the sun, then of course the entire Earth would be in winter at the same time, and the entire Earth would be in summer at the same time. It wouldn't be half and half. What does it have to do with? The tilt of the Earth's axis. And it has to do with flux. So the tilt of the axis means that the sunlight hits the surface area at a different angle at different times of the year. So let's take this example. I'm going to just say that this is the orientation between the sun and the Earth now. The sun's light comes in basically parallel to each other, the rays, because the sun is so far away. So we have sunlight coming to the Earth. And let's pick a point on the Earth. How about right here? We'll pick a little section of the Earth right there. And the sunlight is coming in and hitting that section at a fairly steep angle. So think about this for a second. If you've had a flashlight and a piece of cardboard or paper, and you shine that flashlight directly at the paper when they're perpendicular to each other, the rays are perpendicular to the surface, all of that light ends up in a nice tight circle on the piece of paper. All that energy that the light carries, because light carries energy, gets concentrated on a small area of that paper, and that paper absorbs that light energy. But if you take that paper and you angle it a little bit, then that light that hits it gets spread out over a big oval. And because the light is spread out over a much bigger part of the paper, each little section of the paper doesn't get exposed to as much light, doesn't absorb as much of the energy from the light, and it doesn't get as warm. So in this case, the light is hitting the surface at a very steep angle, and not very much of it is being absorbed because it's covering a lot of surface area of the Earth. Let's take a look at what happens 6 months later, when the Earth has moved around to the other side of the sun. It's 6 months later now, and the Earth has moved to the other side of the sun. And so this section over here that used to be facing the sun at a glancing angle is now over here. And it's facing the sun almost normal to the light coming in. So each section of Earth is being hit with more light, with more concentrated light energy. It absorbs more of that energy, it heats up more. This would be summertime, and this would be our winter. This is for a spot in the northern hemisphere. You can see that if we were in the southern hemisphere, it would be just the opposite. A point over here that's getting a lot of light 6 months later would be over here and not getting much light. So the northern hemisphere and the southern hemisphere, because of the tilt of the axis, have their summers and winters flipped from one another. And it all has to do with the light energy being absorbed by the ground. It all has to do with flux. All right, that was a fun aside, but let's get back to electric flux and Gauss's law. So electric flux is interesting, but it really isn't all that useful by itself. Gauss's law makes it useful because it helps us find electric fields, and that's usually the objective. Gauss's law tells us that the electric flux is proportional to the charge inside of a closed surface. The electric flux through a closed surface is proportional to the charge inside of that surface. And our proportionality constant is epsilon naught. We know what the flux is, the integral of E dot dA. And so this provides that link between the flux and the electric field and helps us find the electric field in very specific cases. So Gauss's law is always true, but it's really only useful in a few cases. It only simplifies life for us in a few situations. One of those is spherical symmetry and cylindrical symmetry. And the last one is infinite sheets of charge. Let's do an example with cylindrical symmetry. And let's pick a situation where we already know how to find the electric field. How about an infinite line of charge? An infinite line of charge, we can do that using the techniques we learned in the previous chapter by integrating over the charge distribution. So we can do it that way, and then we can do it with Gauss's law and check our answer and see which method is easier. Let's take a look at why we have cylindrical symmetry. If we take a side view of our infinite line of charge, here's our line of charge. Let's just make it positive charge. And if we look at it from the side, the electric field is coming off like this. If we look at it from the end, if we rotate this by 90 degrees and we look down the end of the line charge, what do we see? There's our line charge. And we see the electric field lines coming out like this. So we have some cylindrical symmetry here. It's like a cylinder. If we pick a Gaussian surface that matches this symmetry, then maybe we'll have easier integrals to solve. How would I match the symmetry? Well, I would put a cylinder in here that matches the cylindrical symmetry of the problem. I would not put a cylinder like this. That does not match the symmetry of the problem, because you can see that if I did it that way, looking down from the top, the cylinder would be shaped like this, and the electric field would have a different value at each of these points and a different angle at each of those points, and it would be a very difficult integral to solve. The angle's changing, the magnitude is changing. I have to pick a symmetry that matches the problem. I have to orient my cylinder, my Gaussian cylinder, with the axis along the charge distribution like this. And if I look down from the top, what do I see? I see my Gaussian surface looking like a circle, the end of my cylinder. The idea is to find the electric field some distance r away from the charge distribution. We're just going to leave it as a variable. So if r is 2 meters, then we plug in 2 and we find the electric field 2 meters away from our charge distribution. If r is 104 meters, we plug in 104, we get the electric field at that distance away from our charge distribution. We want the electric field as a function of r at some distance r, any arbitrary r, from our charge distribution. So I'm making my Gaussian surface a distance r from my line charge. I want this imaginary Gaussian surface to be at the location where I want to know what the electric field is. So Gauss's law tells me that the flux, which is the integral around the closed every side of the Gaussian surface, every side of my enclosed Gaussian surface of E dot dA is equal to the charge inside over this constant epsilon naught. A cylinder has 3 sides to it. It has a top, it has a bottom, and it has this curved side. So I can split this integral up into 3 integrals. The integral over the top of E dot dA plus the integral over the curved side of my Gaussian cylinder plus the integral over the bottom of my Gaussian cylinder of E dot dA. And all 3 of those together make up the integral of E dot dA over the closed surface. That's what that little circle there means. The integral over the entire closed surface. And this has to equal the charge inside over epsilon naught. Let's take a look at each one of these. The top, we're looking at the electric flux through the surface that makes up the top of my Gaussian cylinder, through this surface up here. Well, you can see the electric field lines never penetrate that surface. They are parallel to the surface, or you could say the area vector would be pointing up and my electric field would be pointing horizontally, so there's a cosine of 90 degrees there between those 2 vectors. E parallel to A, so this is 0. And the bottom is the same. The electric field lines never penetrate the bottom. They just skim along parallel to the surface. So I've got 0 flux through that surface as well. Again, cosine of 90 degrees is 0. Same reasoning for the top as for the bottom. All I'm left with is the integral of E dot dA over the curved surface, the side of my cylindrical shape. Now if I go back and look at my drawings here from the top view, I can see that my electric field is always normal to the surface. So the angle between the area vector and the electric field vector is 0 degrees. The electric field points out and the area vector points in the same direction. So I get a cosine of 0 degrees there. And I've got my electric field is constant. And that just leaves me with the integral of dA, which is just the area. And so this is just E times the area of the side, right? The curved side of the cylinder, Q in over epsilon naught. And what is the area of the curved side of a cylinder? If we have a cylinder like this, and we cut it down the side and open it up, then this is the area of that cylinder. So it's the circumference of that circular end multiplied by the height of the cylinder. This is just going to be 2 pi r h, where h is the height of my Gaussian cylinder. And what does that equal? The charge inside over our constant. Now you might be wondering, how is it that I'm doing the problem and I'm going to solve for the electric field, and it's going to depend on the height of my Gaussian surface that I picked, my imaginary surface that I dreamt up has a certain height to it, and you're going to do the problem and you're going to dream up a different height for your imaginary Gaussian surface. How are we going to get the same answer for the electric fields? We both have to get the same answer. Well, it's because if we choose a different height, we're going to have a different amount of charge inside. If I choose a really long cylinder that has a long height to it, a big height, there's going to be a lot of charge inside. You can see the charge is along this rod here that's inside of that Gaussian cylinder. If you choose a short Gaussian cylinder, you're going to have less charge inside. The charge inside of the Gaussian cylinder is equal to our charge density lambda. Lambda is the charge per unit length, multiplied by that length, which is just the height of the cylinder. So Q in is lambda times h. So I have E times 2 pi r h is lambda times h over epsilon naught. Now you can see that the h cancels out. So if you picked a short Gaussian cylinder and I picked a tall Gaussian cylinder, it doesn't matter. It's independent of our Gaussian cylinder. What it does depend on is r, which we want. We want that dependence to be in there. We want to find the electric field at a distance r away from our line charge. So the electric field is going to be 1 over 2 pi epsilon naught lambda over r. And remember, 1 over 4 pi epsilon naught is our constant k. So we could rewrite this as k as 2k lambda over r. This gives us the magnitude of the electric field. We go back and we look at our picture, we see that the line charge is positive, so the electric field points radially outward. So we could put an r hat or a radially outward. Now we can put r hat because we're in a cylindrical coordinate system. If I was using x's and y's, I would not write r hat there. That wouldn't make any sense. Use the coordinate system that makes the most sense for the problem. So go back and double check, do the integral using the previous techniques by integrating over the charge distribution from negative infinity to positive infinity, and see if you get the same answer.